Alright, good morning, it's Mr. Flint, and we are doing projectile some questions to ask. First, when an object is a projectile, what is the shape of the path that it travels? And the answer is going to be a parabola. Yes, it always takes a parabolic path. And so if you threw a ball up through the air, go up, and come back down. Okay. Now, this picture shows a light blue ball being dropped from rest at the same time a dark ball is shot to the right. What can we figure from this picture? Well, it shows that they are released from the same height, and as they fall, they have the same identical heights. So even if one ball is launched horizontally when it is released, they both hit the ground at the same time. So basically, we can figure out at similar times the balls are at the same height. Okay, and that's the first thing. The second thing is that both balls hit the ground at the same time. And that's key, that it takes the same amount of time for both balls to hit the ground. Now, consider an object shot at an angle so that it travels as a projectile. How is the direction of velocity related to the parabolic path at each point? Well, it is a tangent at each point along that path. So the velocity, the path of the velocity, is a tangent line. Say the velocity is always directed tangent to the path at each point. Okay. Now, what happens to the horizontal component of velocity as the projectile travels? Well, the horizontal component of the velocity does not change. What happens to the vertical component of the velocity as the projectile travels? The vertical component is always becoming more and more negative. And that's because the ball is accelerating in a downward direction. So the vertical component of the velocity is just becoming more and more negative as it accelerates in a downward direction. And you know that acceleration would be negative 10 meters per second squared. So there's our negative acceleration. Now, at what point in the path is the vertical component of the velocity 0? Well, the vertical component of the velocity becomes 0 at the very top of the path, right up here. So at the peak of the path. At what point is the speed of the projectile 0? Well, the speed of the projectile is never 0, so nowhere along this path. Speed is never 0. And we can see that with the arrows here, the vectors there, that the speed is never 0. There's always some velocity as long as that ball is in the air. Okay, when we have that. Now, a person throws a ball in such a way that the speed is 0 at one particular point in the path. How did the person have to throw the ball? Well, the ball would have to be thrown straight up in the air and then come straight back down. Okay? So go straight up and straight down. And at the very top of the path right here, the speed of the ball would be 0. So how did the person throw the ball? Straight up and straight down. Now, projectile travels from point A to point G as shown below. Find the components of the velocity vector at point A, then determine the components of the velocity vector at every other point. Use the fact that each point occurs 1 second after the previous. Also use acceleration equals 10 meters per second squared. So we can do that if we know that the initial velocity is 50 meters per second, then the initial velocity in the x direction, and let's do velocity. I used the wrong letter, not x. I need to use velocity. Okay, so the initial velocity in the x direction, okay, is going to be equal to the initial velocity multiplied by the cosine of the angle. So we would take 50 times the sine of 37, and that would give us 40 meters per second. So that would be 40 meters per second. And then that remains constant. Once we know that, the horizontal component never changes. It is always the same. So it's still going to be 40 meters per second here. Still going to be 40 meters per second here. It's 40 meters per second here. 40 meters per second here. Here. And finally also here. So that component remains constant. Now, the other component, we need to find it. The initial velocity in the y direction, and that's going to be the initial velocity times the sine of the angle. So let's plug in our numbers here. The initial velocity was 50, and that's given to us right there. Okay, times the sine of the angle, 37 degrees, and that gives us 30 meters per second. Okay. So this component here is going to be 30 meters per second, whereas the horizontal started at 40. The vertical is going to be at 30 meters per second. Now, at the next second, what will it be? Well, since it's accelerating, it will be 10 meters per second less, so it'll be 20. And right here, this vertical component will be 10. And then here it's going to be 0. There's no vertical velocity at that point. It's all horizontal. Then we're going to see the opposite start to happen. We're going to get a 10, and we could consider this a negative 10 meters per second. Negative 20 meters per second here. And finally down here, I'll write it over here to the side, negative 30 meters per second. Now, when an object travels as a projectile, what type of motion occurs in the horizontal direction? Well, if we come back and we look at that, we have constant velocity in the horizontal direction. It's always 40 meters per second for A, B, C, D, E, F, and G. It doesn't change. So we say that we have constant velocity. Oops. In the horizontal direction. We've got constant velocity there in the horizontal direction. All right, now let's look at the vertical. What type of motion occurs in the vertical direction? Well, if we go back and we look at our numbers, we can see that it started at 30 meters per second, went to 20 meters per second, to 10 meters per second, to 0, to negative 10, to negative 20, to negative 30 meters per second. So we can see that it is accelerating in the vertical direction. So we get constant acceleration in the vertical direction. And you know that acceleration is approximately 10 meters per second squared. Now when we're working in lab in the real world, we'll use 9.8 meters per second squared. Okay. Now let's analyze the motion graphs of this. Okay, if we want the position versus time graph for this, since we have acceleration here, the position versus time graph for this in the x direction is going to be constant, so that would be graph D. So we should see graph D there. Okay, and the vertical direction, the position versus time, it's just going to mirror that, so it's going to be graph E. Okay. Now, as we look at velocities, let's talk about what's happening to the velocity horizontally. Well, horizontally, the velocity is not changing, it's staying constant. So where do we see a constant velocity? Well, we see constant velocity with C. And if we have constant velocity, then in the horizontal direction, we're not going to have any acceleration, and so zero acceleration would be represented with graph A. Now, let's get back to the vertical. The vertical, we can see, is this parabola, so, and the velocity is always changing. So what graph represents it's changing? Well, graph B does a great job of doing that. And then we get constant acceleration if we have that, and so since this is a negative slope and we've got constant negative acceleration, we should see graph F. Okay, so those are our graphs for this. And we will eventually get to do a lab that does that shows us those things. That's it for now. We're going to have another screencast where we actually work out practice problems.